Lessons 7-5 to 7-6. Apply the trigonometric ratios to find missing sides. By the end of today's lesson, we will be able to successfully use sine, cosine, and tangent ratios for indirect measurement. So let's begin with sine. The sine of an angle is the ratio of the length of the leg opposite the angle to the length of the hypotenuse of a right triangle. So I will write opposite over hypotenuse. So A over C. So sine A. So A will represent the degree here. Will equal to opposite A over hypotenuse C. And sine B would equal to opposite over hypotenuse C. So B over C. And the second one we have is cosine. Cosine is defined by an angle that is the ratio of the length of the leg adjacent, meaning next to, the angle to the length of the hypotenuse. So we have cosine A equal to adjacent over hypotenuse. So adjacent would mean this length B over hypotenuse C. And then for cosine B, we'll take A and put that over hypotenuse C. And then for the third one, we have tangent. The tangent of an angle is the ratio of the length of the leg opposite the angle to the length of the leg adjacent to the angle. So tangent A is defined by opposite over adjacent. We have A over B. And then for tangent B, angle B, we would do B over A. These formulas can be remembered by SO, CA, TOA. That means SOH, CAH, TOA. Now let's try some examples here. And write each trigonometric ratio as a fraction and as a decimal rounded to the nearest hundredths. So then, for the first one, for sine J, so to look at this angle, and remember sine is opposite over hypotenuse, so we have to take 60 and put it over 61. And by using your calculator, this would equal to approximately 0.98. And for the next one, we have cosine J. If we look at J here, cosine is equal to adjacent over hypotenuse, so we have 11 over 61. So that would equal to about 0.18. And then we have tangent J. That will be opposite over hypotenuse, so that's 60 over 11. About 5.45. And now we have sine K. Sine K will be opposite over hypotenuse, 11 over 61. that's about 0.18. And then cosine k, we'll take adjacent over hypotenuse, will be 60 over 61, about 0.98. And tan k, 11 over 60, about 0.18. Example 2 would like you to use your knowledge of special right triangles to write the trig ratios for a 30, 60, 90 triangle. So let's look at from part A here. Sine 30 degrees would be s over 2s. And if we simplify this, it would be half. And cosine 30 will be s square root of 3 over the hypotenuse, which is 2s. So when we simplify this, it's square root of 3 over 2. And then we have tangent 30 degrees. So that would be opposite s over the adjacent leg. So that would be s square root of 3. And now we can't have a square root in the denominator, so we're going to have to multiply by square root of 3 over square root of 3. And then we can cancel the s. So this would be square root of 3 over 3. And sine 60, opposite over hypotenuse. So that's s square root of 3 over 2s. And then cosine 60, adjacent over hypotenuse, so that's s over 2s. That's 1 over 2. And then we have tangent 60 degrees, which is opposite over the adjacent leg, so that's s square root of 3 over s, which is just square root of 3. Example 3, use your knowledge of special right triangles to write the trig ratios for a 45, 45, 90 triangle. So when we have sine 45, it would just be, well, we need to first calculate the length of the hypotenuse, which is just s square root of 2. So we could take the opposite length, we would take this, look at this angle, be s over s square root of 2. And if we look at this angle, it will be the same thing, s over s square root of 2. And then I'm going to multiply by square root of 2 over square root of 2, because we cannot have a square root in the denominator. We can cancel this out, and that's it. And then cosine 45 degrees would just be represented by adjacent length over hypotenuse, which is s over s square root of 2. And again, we need to multiply by this. And then tangent 45 degrees will be just s over s, which is just 1. Okay, and for the next one, find each length rounded to the nearest hundredths. And my suggestion here is do not round until your final step. Make sure your calculator is in degree mode if you're using either a scientific calculator or a TI. So for the next one, part A here, and I would like to find the length of BC. In this case, I have to use tangent. So tangent 15 degrees would equal to 10.2 over, I'm just going to label this as x. So to solve for x, this would be x times tangent 15 degrees equals 10.2, and x would equal to 10.2 divided by tangent 15 degrees. And then using your calculator, all you have to do is type in 10.2 divided by tan 1.5, and you should get about 38.07 as your approximate length. And for part B, we have, let's see, we need to find QR. So QR is the opposite of angle P, and we're given the hypotenuse, so we can use sine. Sine is defined by opposite over hypotenuse. X would equal to 12.9 times sine 63 degrees, and go ahead and multiply 12.9 by sine 63 degrees, and you should get about 11.49. And for FD here, we're given the length of an adjacent side, so cosine 39 degrees equals adjacent over hypotenuse 20 over x. So x would equal to 20 divided by cosine 39 degrees. And this would be equal to about 25.74. So go ahead and double check this using the calculator. And then we have part D. We need to find the length of DF. And we're given angle D, and we're given the opposite length of angle D, and we need to find the length of the hypotenuse, so we need to use sine. Sine 51 degrees is equal to the opposite over the hypotenuse x. So x would equal to 17 divided by sine 51 degrees, and that would be about 21.87. Okay, let's do one more here. We want to find ST, and we're given 42 degrees for angle T, and then we're given the hypotenuse. And we want to find this one. So that would be, we're given an adjacent length, hypotenuse, and we need cosine. Cosine 42 degrees would equal to the adjacent length over the hypotenuse of 9.5. And then x is about 7.06 inches. Well, I need to label all of these meters, and the ones above as well. Example 5. The glide slope is the path that the plane, A plane, uses while it is landing on a runway. The glide slope usually makes a 3-degree angle with the ground. So I'm going to draw the glide slope and 3-degree angle with the ground. And a plane is on the glide slope and is 1 mile, which is about 5,280 feet from touchdown. Use the trig ratio to find the plane's altitude to the nearest foot. So this is what we need to find. So this is 5280. So we have the opposite. We're looking for the opposite length from 3 degrees, and we have the length of the hypotenuse. So we're going to have to use sine. 3 equals x over 5280. So x will be about 276 feet.